Here's a strange fact to sit with before we go any further. The universe might not actually have an edge at all. Not, we haven't found it yet, not, it's too far away to see. As far as the best cosmological models we have can tell, there may be no boundary out there to reach in the first place. No wall, no edge, no shoreline, where the universe simply stops. And if that sounds like it should make the question easier, it doesn't. It makes it stranger. Because even setting aside whether an edge exists, there's a second, completely separate reason humans can never reach it. One that has nothing to do with how big the universe is, and everything to do with how fast it's growing. Space itself is expanding, and it's accelerating as it does, which means that no matter how fast we ever learn to travel, there are already parts of the universe we will never, under any circumstances, be able to reach. Not with today's rockets, not with some future engine humans haven't invented yet, not even, according to the physics, with a ship that could somehow travel at the speed of light itself. Let's start with the part that trips almost everyone up first, the difference between the universe and the observable universe, because those two phrases get used interchangeably all the time, and they mean completely different things, a distinction that turns out to matter enormously once you start asking what it would actually take to travel there. The observable universe is the portion of everything that exists which we can, in principle, actually see, meaning light from it has had enough time to travel all the way to us since the universe began. Based on the most current measurements, the universe is about 13. 8 billion years old, a figure refined over decades through multiple independent lines of evidence, from the cosmic microwave background to the ages of the oldest known stars. A natural first guess would be that the observable universe should therefore be a sphere about 13. 8 billion light years in radius, since that's simply how far light could have traveled in that amount of time. But that guess turns out to be wrong, and the reason why is the entire key to this whole story. Space itself has been expanding this entire time. While a photon of light from some distant galaxy was making its 8 billion year journey toward us, the space it was traveling through was simultaneously stretching, carrying that galaxy even farther away from where it was when the light first left it. Account for that stretching, and the actual current distance to the farthest light we can see turns out to be roughly 46. 5 billion light years, not 13. 8 billion, even though that light has technically only been traveling for 8 billion years. The boundary, the outer edge of everything whose light has had time to reach us, is called the particle horizon, and it defines the observable universe. But here's the crucial point. The particle horizon isn't a wall. It isn't the edge of everything that exists. It's simply the edge of everything we're currently capable of seeing. A horizon defined entirely by the finite speed of light and the finite age of the universe. The same way the horizon at sea isn't the edge of the ocean, just the limit of how far your eyes can see across a curved surface. Beyond our particle horizon, the universe almost certainly keeps going, with more galaxies, more stars, more of everything, stretching out for a distance nobody can currently measure because their light simply hasn't had time to reach us yet. It helps to picture this with a concrete comparison, because the abstraction of space itself stretching can be hard to hold on to. Imagine standing on the surface of a balloon that's slowly being inflated, with small dots drawn all over it representing galaxies. If you're one of those dots, every other dot appears to move away from you as the balloon inflates, not because any of the dots are crawling across the rubber surface, but because the surface itself, the space between the dots, is stretching in every direction at once. Light traveling from one dot to another has to cross that same stretching surface, and the longer the journey takes, the more additional stretching happens along the way, which is exactly why a photon that left a galaxy 8 billion years ago ends up having crossed a gap that's now grown to roughly 46. 5 billion light years, even though the photon itself never moved faster than light for a single instant of that entire journey. Nothing about that scenario breaks any law of physics. It simply means that distance and travel time, which feel like the same thing in ordinary, everyday experience, come apart from each other dramatically once you're dealing with distances and timescales this large, a gap that only widens the farther back in cosmic history you try to look. So if the observable universe isn't the whole universe, how big is the whole thing actually? This is where cosmologists have to be honest about the limits of what we can currently know. Based on measurements of the curvature of space itself, largely drawn from detailed studies of the cosmic microwave background, the faint leftover radiation from shortly after the Big Bang, the universe appears to be geometrically flat, or extremely close to it, to within a very tight margin of measurement error. A perfectly flat universe, under the standard equations of general relativity, is either infinite in extent or so close to infinite that we may never be able to tell the difference using any instrument humanity could realistically build. If the universe genuinely is infinite, then the question, how far away is the edge, doesn't just have a large answer. It has no answer, in the same way asking how far you'd have to walk to reach the edge of an infinite flat plane doesn't have a numerical answer either. There's a real possibility, taken seriously by working cosmologists, that the phrase edge of the universe describes something that simply doesn't exist. The same way the edge of all the whole numbers doesn't exist, no matter how far you keep counting. It's worth being clear about what flat actually means in this context, because it's a term borrowed from geometry that doesn't map cleanly onto everyday intuition. It doesn't mean the universe is shaped like a flat sheet of paper floating in some larger space. It refers to how parallel lines, triangles, and angles behave across large distances within the universe itself. In a flat universe, two parallel beams of light will stay exactly parallel forever, and the angles of a sufficiently large triangle will add up to precisely 180 degrees, exactly the rules you learned in school geometry. Cosmologists can actually test this directly by studying the precise angular size of temperature fluctuations in the cosmic microwave background, since a curved universe would distort those angles in a measurable, predictable way. The results, refined across multiple missions including the Planck satellite, have consistently come back flat, or so close to flat, that any curvature must be extraordinarily subtle, smaller than current instruments can detect. A universe that's flat, or curved so gently that we can't measure the difference, is exactly the kind of universe general relativity says should either be genuinely infinite or so vastly larger than the observable portion that the practical difference is meaningless for any civilization confined to a single, ordinary-sized galaxy. Even if you set that entire question aside and just focus narrowly on the observable universe, the part we know for certain exists. Because we can literally see it, there's still a second independent reason we could never travel there. And this is the part that really changes how you think about space travel. It comes down to a discovery made back in 1929 by astronomer Edwin Hubble, who found that distant galaxies aren't just moving away from us. They're moving away from us faster the farther away they are, in a remarkably clean, consistent relationship now called Hubble's law. Double the distance to a galaxy, and you roughly double its recession speed. That relationship holds for relatively nearby galaxies, well within the range, where speeds stay far below the speed of light. But follow that same relationship out far enough, and the implied recession speed eventually crosses the speed of light itself. That sounds like it should be physically impossible, and if we were talking about a spaceship or a particle physically moving through space, it would be. Nothing with mass can travel through space faster than light, according to special relativity, full stop. But galaxies receding from us due to cosmic expansion aren't moving through space in that sense at all. They're standing still, relatively speaking, while the space between us and them stretches. It's the fabric of space itself doing the moving, not the galaxies traveling through it, and general relativity places no speed limit whatsoever on how fast space itself can expand. This distinction isn't a semantic trick physicists use to get around the speed limit. It's a genuinely different physical phenomenon, and it means that right now, today, there are galaxies receding from Earth faster than light, without violating a single law of physics. It's worth pausing on how counterintuitive that really is, because it runs directly against the one physics rule most people learn early and remember clearly. Nothing outruns light. That rule remains completely intact here. A rocket ship, a radio signal, a beam of light itself, none of them can ever travel faster than light through the space immediately around them. Locally, at any given point along their journey, a rule that is held up under every experimental test physicists have ever devised. What Hubble's law describes is something else entirely. The cumulative effect of countless tiny bits of space, each expanding at an unremarkable, physically unrestricted rate, adding up across a large enough total distance until the combined recession speed crosses the speed of light. No single patch of space anywhere is expanding faster than light. It's only when you sum up the expansion happening across billions of light years of intervening space, all at once, that the total recession speed can exceed it. Special relativity governs local motion through space. It says nothing at all about how fast space itself, considered as a whole, is permitted to grow. The distance at which that crossover happens, where a galaxy's recession speed due to cosmic expansion equals the speed of light, is called the Hubble radius. And based on the most precise recent measurements of the universe's expansion rate, it sits at somewhere around 14 to 15 billion light years from Earth. Here's where things get genuinely current and genuinely unresolved. In April 2026, an international collaboration called the H0 Distance Network published the most precise direct measurement yet of how fast the local universe is expanding, combining multiple independent methods, Cepheid variable stars, red giant branch stars, and carbon stars, cross-checked using both the Hubble Space Telescope and the James Webb Space Telescope to cut through cosmic dust that had blurred and complicated earlier ground-based measurements for years. The result? A Hubble constant of 73, 50 kilometers per second per megaparsec, accurate to just over 1%, one of the tightest, most carefully cross-validated measurements of this kind ever achieved. The problem is that this number doesn't match the value predicted by measurements of the early universe, based on the cosmic microwave background, which consistently comes out closer to 67, 2 kilometers per second per megaparsec, a gap that has now persisted and sharpened across nearly a decade of increasingly precise independent measurements. That mismatch is known as the Hubble tension, and rather than resolving as measurements get more precise, it's been getting worse. Researchers involved in the April 2026 study were direct about what that means. This isn't just a new number for the expansion rate. It suggests something fundamental might be missing from our current model of how the universe actually works. A possibility serious enough that it's now treated less as a measurement error to be ironed out and more as a genuine crisis for the standard model of cosmology itself, one that upcoming instruments like the recede, Rubin Observatory, and the Nancy Grace Roman Space Telescope have been specifically tasked with helping to resolve in the years ahead. Whichever exact number turns out to be correct, the basic physical picture holds either way. Somewhere out past roughly 14 or 15 billion light years, space is expanding fast enough that objects out there are receding from us faster than light can travel. Anything beyond that distance is, in a very real sense, permanently out of reach for physical travel, because no matter how close to the speed of light a spacecraft managed to go, it could never outrun space itself expanding away from it faster than it could cross that space. A conclusion that holds regardless of which side of the ongoing Hubble tension debate eventually turns out to be correct. But it actually gets worse than that, and this is where dark energy enters the picture. Cosmologists have known since the late 1990s, through observations of distant supernovae, that the universe's expansion isn't just continuing, it's accelerating, driven by a mysterious force researchers call dark energy, which makes up roughly 68% of the total energy content of the universe, despite nobody fully understanding what it actually is at a fundamental level. Because that acceleration is baked into the expansion itself, there's a second, even more restrictive boundary beyond the Hubble radius called the cosmological event horizon. This marks the point beyond which light emitted right now, at this exact moment, from a distant galaxy, will never reach Earth, no matter how much time passes, because the space between us and that light is expanding fast enough and accelerating fast enough that the light can never close the gap. Based on the standard cosmological model, that event horizon sits at roughly 16 billion light years away today. Anything beyond it isn't just currently unreachable, it's permanently, irreversibly unreachable for us and for any future civilization descended from us for the entire remaining lifetime of the universe. It's worth understanding just how strange dark energy is as a physical concept, because it's easy to say the word without appreciating how little we actually know about it. Ordinary matter and radiation, the stuff that makes up stars, planets, gas, light, and even the mysterious dark matter that outweighs all visible matter combined, all become more diluted and exert weaker gravitational influence as space expands and spreads them thinner. Dark energy behaves completely differently. Its energy density appears to stay constant even as space expands, which means the more the universe grows, the more total dark energy there effectively is, driving the expansion to accelerate rather than slow down the way gravity alone, acting on ordinary matter and radiation, would otherwise predict. Astronomers only confirmed this behavior in 1998 through independent teams studying distant type Ia supernovae, a discovery significant enough to earn a Nobel Prize in Physics in 2011, awarded jointly to Saul Perlmutter, Brian Schmidt, and Adam Rees for overturning what had until then been the widely assumed expectation that cosmic expansion should be gradually slowing down under its own gravity, not speeding up. Nearly 3 decades later, despite dark energy making up roughly 2/3 of everything in the universe by energy content, physicists still don't have a confirmed explanation for what it actually is at a fundamental level, whether it's a genuine property of empty space itself, some new field nobody has directly detected, or evidence that our equations governing gravity on the largest scales need to be revised. Whatever the eventual answer turns out to be, its practical effect is unambiguous, and it's the single biggest reason the universe is actively working against any future attempt to reach its farthest regions. And that boundary isn't static. Because dark energy keeps driving the expansion faster over time, the cosmological event horizon effectively closes in around us as the eons pass. Galaxies that are currently visible, currently within our reach in principle, will eventually cross that boundary and vanish from view forever, their light redshifted into oblivion before it can complete its journey to us. Astronomers estimate that in the extremely distant future, tens of billions of years from now, an observer in the Milky Way's remnant will only be able to see the handful of galaxies gravitationally bound closely enough to us to have resisted being swept away by the expansion, essentially the local group, while every other galaxy in the observable universe redshifts out of detectability entirely, disappearing not because they cease to exist, but because the space between us and them will have stretched too fast for too long for their light to ever complete the crossing. This has a genuinely eerie implication for anyone doing astronomy far enough in the future. Right now, in 2026, we happen to live at a moment in cosmic history where we can still detect light from galaxies formed relatively soon after the Big Bang, look out at thousands of other galaxy clusters, and piece together a reasonably complete picture of the universe's large-scale structure, its expansion history, and its likely origin. Some cosmologists have pointed out, only partly as a thought experiment, that a civilization arising far enough in the future, say 100 billion years from now, would look out at the night sky and see almost nothing beyond their own galactic neighborhood. No cosmic microwave background left detectable, no distant galaxies to study, no observational evidence of the Big Bang at all, because every one of those signals will have already redshifted permanently out of reach long before that point. Such a civilization might reasonably conclude that their own galaxy is essentially all that exists, a static, isolated island in an otherwise empty universe, with no way to observationally reconstruct the expanding, structured cosmos we can still study clearly today. We happen to be living during an unusually favorable observational window in the universe's multi-trillion-year timeline. And that window is slowly, permanently closing, one redshifted galaxy at a time. Now, layer human technology on top of all of that, and the scale of the problem becomes almost comic. Voyager 1, the fastest, farthest traveling object humanity has ever built, launched in 1977 and has been accelerating away from Earth, using gravitational slingshots from Jupiter and Saturn ever since. After 49 years of continuous flight, it has covered a little over 165 astronomical units, roughly 15 billion miles. That sounds enormous, and by the standards of human engineering, it absolutely is. But converted into the units this conversation actually needs, the distance comes out to roughly 0.226 light years. The observable universe, just the part we can already see, spans roughly 93 billion light years across. At Voyager 1's current speed, reaching even the edge of what we can currently observe, setting aside the expansion problem entirely, would take longer than the current age of the universe repeated many thousands of times over. And that's without even accounting for the fact that the expansion itself means that boundary is constantly moving farther away, faster than any chemical rocket, or even a theoretical antimatter drive, could ever hope to close the gap. To make that comparison land a little harder, consider how it stacks up against the fastest speeds humanity has ever actually managed to achieve with anything more substantial than a subatomic particle. NASA's Parker Solar Probe, which dives repeatedly close to the Sun using its gravity for repeated speed boosts, has reached speeds exceeding 430,000 miles per hour, making it, by a wide margin, the fastest human-made object ever built. Even at that blistering pace, dramatically faster than Voyager 1's roughly 38,000 miles per hour, it would still take a spacecraft traveling that fast many tens of thousands of years just to cover a single light year. The nearest star system beyond our own sun, Alpha Centauri, sits about 3 light years away, and at Parker Solar Probe's top speed, a one-way trip there would take somewhere in the ballpark of 6,000 years. Scale that same math up to a target 46. 5 billion light years away, the current radius of just the observable universe, and the travel time stretches into numbers so large they stop being meaningful as anything other than an illustration of scale, tens of trillions of years, dwarfing not just the current age of the universe, but any timescale relevant to human civilization, biological evolution, or even the expected lifespan of most stars still burning today. Push the thought experiment to its absolute physical limit, and the conclusion doesn't change. Imagine a future spacecraft that somehow, through some technology none of us can currently picture, managed to travel at exactly the speed of light. Even that ship, moving as fast as anything in this universe is physically permitted to move, could never reach a galaxy that lies beyond the cosmological event horizon, because the space between the ship and that galaxy is expanding faster than the ship could ever cross it, no matter how long the journey continued. It's not a limitation of engineering. It's a limitation built directly into the geometry and expansion rate of the universe itself, the same physical law that governs everything from the orbit of the moon to the behavior of light inside a black hole. There is no future propulsion breakthrough that fixes this because the problem was never about speed in the first place. It's about the space itself growing between here and there faster than anything could ever cross it. This is also where a lot of popular science fiction quietly runs into trouble without most viewers ever noticing. Concepts like wormholes or theoretical warp drives, the kind that occasionally show up in serious physics papers as mathematically valid solutions to Einstein's equations, generally work by manipulating the geometry of space itself rather than moving an object through space in the conventional sense, which is exactly why they get proposed as loopholes around the light speed limit in the first place. But even setting aside the enormous currently unsolved engineering problems those concepts would require, most notably a form of matter or energy with negative mass or negative energy density that has never been confirmed to exist in any usable quantity, they don't actually solve the cosmological horizon problem discussed here. A warp bubble might, in principle, let a ship cross a fixed distance faster than light would take to cross that same distance under normal conditions. It does nothing to change the fact that the destination itself, if it lies beyond the cosmological event horizon, is a point in space that is receding from us at an ever-accelerating rate, driven by the expansion of the universe as a whole, a problem that exists at a much larger, more fundamental level than any local propulsion technology could address. The universe isn't just far. It's actively working against the very idea of being fully explored by anyone, using any method physics currently allows us to imagine. There's a specific, almost poetic detail buried inside this whole picture that's worth sitting with before we wrap up. Because the observable universe is defined by how far light has had time to travel since the beginning, and because that boundary keeps expanding as more time passes, the observable universe itself is technically growing, roughly 1 light-year larger in radius for every year that passes, just from new, older light finally completing its journey to us for the first time. At the exact same time, thanks to accelerating dark energy-driven expansion, the portion of the universe that will ever be reachable, or even theoretically visible to us in the deep future, is simultaneously shrinking, as galaxies currently within our cosmological horizon slowly redshift their way toward permanent invisibility. We are, in other words, living through a strange, slow-motion crossover point in cosmic history, watching new light arrive from ever farther away, while the truly reachable portion of the universe quietly closes in around us, a process that will continue for the rest of time, long after every star currently burning has gone dark. So why will humans never reach the edge of the universe? Not because our engines aren't good enough yet, though they certainly aren't. Not because the distances are merely inconvenient, though they absolutely are. It's because the target itself may not exist as a fixed destination at all, and even the part of the universe we can define with any confidence is, in a very real physical sense, retreating from us faster than anything could ever catch it. Every galaxy we can currently see through our best telescopes, every faint smudge of ancient light captured by Webb or Hubble, represents a place that human beings, or any descendant of human beings, however advanced, will never physically visit, never send a probe to, never receive a returned signal from once it crosses that final permanent horizon. That's not a failure of ambition or imagination. It's a fact about the shape and behavior of the universe itself, discovered not through speculation, but through decades of careful measurement, refined as recently as this year. And it's arguably one of the strangest, most genuinely humbling truths in all of modern physics, that the very act of looking farther into space means looking at a universe that is, in the most literal sense possible, pulling itself apart faster than we could ever hope to follow. There's a strange kind of comfort hiding inside that conclusion too, if you sit with it long enough. It means the observable universe we do have access to, the roughly 93 billion light-year bubble of galaxies, stars, and light currently within our reach to study, isn't a small, disappointing fraction of some larger prize we're failing to claim. It's simply the entire scope of what exploration and discovery could ever mean for any civilization bound by the physical laws of this particular universe. Within that bubble alone sit hundreds of billions of galaxies, each with hundreds of billions of stars, an amount of genuine, physically reachable mystery so vast that no civilization, however long-lived, could ever hope to run out of things left to learn, long before the deeper question of what lies beyond the cosmological horizon would ever become the limiting factor. Put simply and directly, the boundary we can never cross turns out to be so unimaginably far away that it was arguably never really the actual point of exploring in the first place. If you want a deeper breakdown of the Hubble tension, dark energy, or what the far future of an expanding, accelerating universe actually looks like for whatever's left of life by then, let me know in the comments, subscribe if you want to be here for the next one, and I'll see you in the next video.